Hello, this is Christian Cruz, and I am partnered with Abner Beltran for the pilot project of CE6370. First, I'll discuss the hard processor that runs the C application. The first features that I implemented were the randomly generated encryption keys and user input provided plaintext. And those two features were very abstract on the hardware. So in order to help have faster iteration times to allow more room for testing and verification, I had modified the make file build system so that I can pick whether to compile for my local computer or to cross compile for the FPGA. The idea being that it would be quicker for me to compile and run it on my computer without having to transfer the files to the FPGA. And once I saw that the logic and behavior was satisfiable enough to meet my requirements, I would then cross compile and test it on the actual FPGA and check for compatibility purposes and make sure that it would run just fine. So here's what their implementation looks like in practice from the console output. So for the user input provided plain text, it's simply just a series of 16 bits separated by space or new lines. As for the randomly generated encryption key, this was done by reading a series of generated bytes by reading this file right here. It's the dev urandom file. This is available in the Unix environment. Now, part of the assignment was to implement decryption. Um, I did note that for the forward encryption, the routines were already implemented and given to us, and so utilizing AI assistance with Microsoft Copilot, I was able to generate the routines and even reuse some of those functions from forward encryption to implement decryption. So for instance, you can see that it's making use of the key expansion and the add round key functions. And essentially what all it's doing is that it is undoing the order of operations of the forward encryption process. So for instance, the inverse shift rows functions is undoing the steps from the shift rows functions respectively that was performed during forward encryption. And what, from a high level explanation is what this is doing is that it's essentially using inverse matrices to undo the operations and mathematics that was performed during forward encryption. And this is what it looks like here in the console output. Um, so if you look at the ciphertext, this is the encrypted result. This was given to us, and this is the implemented decrypted result, which matches perfectly with our input provided plaintext.
So starting off with the AES encryption, we'll get the input from HPS. That includes the encryption key, plaintext, and a separate control variable, AES start, to let the FPGA know that it's ready to start the AES encryption. So we'd get that through the AXI interface, and then we'd pass that on to the AES separate Verilog module, which is instantiated inside our GHRD top, which is how we communicate with the HPS. So once we are able or get a post start, then it goes through remaining logic, which includes the finite state machine, the AES encryption or the combinational round logic, and that would output the ciphertext, which would then get sent to the HPS. So here on the right, you can see some of the FSM and combinational round logic that we used. Once we get a post start and it's not busy, otherwise we are in the first round, it would set the plaintext and the key to the corresponding variables, which would then get sent to the combinational round logic, which is where it begins the substitution, the shifting rows, and the mixing columns. That's only for the first round. Technically, it also encompasses the busy, which is when we are not starting anymore and it's already going through the round logic. But once it reaches the final round, it will send a done signal, and that's just to let the HPS know that it's ready to read the ciphertext. Some of the PIO peripherals that we used include the encryption key that we had to make in the platform designer, the plaintext, and the ciphertext. We had to split it into four 32-bit segments since the max width bit of the PIO peripheral is only 32 bits. So that corresponds to the key 0 all the way to key 3, and the same for plaintext and ciphertext. The key and plaintext were the inputs from the HPS. We sent the ciphertext as an output to the HPS, and the other control signals I mentioned before, PIO done, just to let the HPS know that the AES encryption process was completed and it's ready to read the ciphertext. The other one was the AES control, which was again to let the FPGA know that it has received the encryption key and the plain text from the HPS and it's ready to start the AES encryption. So the base addresses that we used were increments of 10. That way we didn't have any overlap, and that was sent to the header file or the HPS0, I believe, just to let the um, C code know where the memory mapped addresses were. We synthesized the report, and these are the resources that the FPGA used. Originally, we intended to do the AES encryption process inside the top file, the GHRD top. Unfortunately, it let each pin be known as a separate pin, thus we had more pins than we needed, and the FIDO report didn't synthesize. So we had to create that as a separate Verilog file, which we then used internal wires and instantiated that inside to be able to have the GHRD top synthesize. That way we don't have as many pin usage that wouldn't let the report or the HTTL synthesize. We didn't have any constraints in the ALM, register, or RAM blocks, so the report used as much as it wanted, and we did only have the one constraint with the clock, so the max frequency, the minimum was going to be the 50 megahertz, so we were able to meet that. This is a test bench simulation, which shows the AES 128-bit standalone Verilog file showing that it works. Um, you can see the known key and plain text that were hard-coded in the Verilog file. We sent a post cert, which then started the AES encryption. Once the AES encryption was done, it would send the done signal back. This is the simulation result at the bottom, which you can see matches the expected ciphertext, showing that the encryption works. You can see the AXI interface here. The PIO external connections are what we connected to the internal wires in the GHRD top, which would then get sent to the AES. PIO peripherals would be what connected to the PIO external, and that would also connect to the lightweight HPS to FPGA AXI bridge, which connected to our HPS.
Okay, I will now explain how the FPGA and the HPS both interact with each other and how the design includes both of them for full system interaction and communication. So this is a sequence diagram showing the process and their interactions. First it starts with the user providing the plain text. The HPS then generates a randomized encryption key, produces the encrypted ciphertext, which is to be used as a golden reference to compare for later. That was especially useful for the development process. And then it would write the plain text encryption keys to the addresses per the PIO configurations made in Quartus for the FPGA's inputs. After that, we figured that we need some kind of synchronization step. So we have a dedicated bit for signaling to the FPGA that its inputs are ready. And this is the AES control bit. So once that is high, or once it's pulsed long enough, then the FPGA will start performing its encryption routines. And when that's done, it would then also give us its own dedicated PIO done bit to signal to the HPS that the output is ready for it to read. So this is essentially some kind of handshaking process. So once the inputs are generated, written, and ready, it will signal to the FPGA. FPGA will encrypt. It will then return an acknowledgement saying it's ready, so then the HPS can read the resulting encrypted ciphertext from its given PIO address. And you can see most of the process implemented here in the console output. What you see in the top section here, those are some debugging print statements that we had. So we wanted to make sure that we were in fact reading and writing to and from between the HPS and the FPGA. So in this step, for instance, this is a step where we're sharing the key or writing the key to the input PIO for the FPGA. So this is the encryption key that we wanted to write at that moment. And after we write it, we would immediately read it back for verification. And this is the readback here. This is straight from the PIO address. So as you can see, all of the readbacks match perfectly with the values that we intended to write with. So that means the FPGA weren't is successfully confirmed to be receiving the proper inputs from the HPS. You can see that we raised our control bit here, and that eventually this is the part where we start waiting for the PIO done bit from the FPGA, and we receive that event, and then we start reading the ciphertext. However, for some reason, the resulting encrypted output is not matching our expectations. I suspect that this may be due to a timing error, perhaps. As demonstrated earlier, the HPS C application and the FPGA have both been confirmed to function and tested to work successfully in their own environments, whether it's with a golden reference or with example values or with the FPGA's test bench simulation. So there must be some kind of issue with getting both of these components to communicate with each other, and I suspect that it may be some small minor bug with timing. So now in the bottom right corner you will see the full console output. This time we have the debugging print statements removed for the sake of meeting the format requirements per the assignment instructions. So this is the user provided plaintext, which matches with our decrypted plaintext here. I included it just to be sure to demonstrate that the HPS can in fact support decryption, so that is successful, as well as we have the expected ciphertext that should have been matching here. Now I will say that this value here in the first 32-bit word, that is from a configuration that was made through Quartus. I wanted to be sure that we could read the output from the FPGA and make sure that that was not the issue up here above. And so in the platform designer, when you configure the PIOs, you're given a field option to set a default value for when the system resets. So I added our classic hex value of dead beef, and this is the result. So the above screenshot confirms that we can read from the FPGA, and the above screenshot confirms that we can write to the FPGA, and the bottom screenshot confirms that we can read from it. So the system is working as intended, with the minor description of the actual intercommunication that will actually kick off the process. But otherwise, the individual components are working successfully. Hello, I will now commence the project demonstration. So let's just have some pre-written sample values for the plaintext. I've already cross-compiled and transferred my executable to the FPGA target device. I'll provide the value for the plaintext, and you can see that it's being read correctly here, and the software generated ciphertext is successfully decrypted back to the user provided plaintext values. You will see here that we are unable to produce a good ciphertext from the FPGA, and therefore we do not have a plaintext that we can produce out of that. So we have this issue persists despite the FPGA having been confirmed to successfully perform the AES encryption process through a test bench simulation, as well as despite having confirmed the reading and writing operations working successfully between the hard processor and the FPGA. So this means that there may be some kind of disconnect somewhere with how the synchronization variables, signals, variables, and data is being passed around with the potentially the Verilog files that are using the AES module and integrating it with the PIO at a higher level. Who knows? I suspect that it's something very small, and I feel that we are very close. Now we can test this with another value that I had pre-prepared for the sake of time. And there you go. The user provided plaintext is here, read successfully, decrypted successfully on the hard processor. We're still seeing the default value of dead beef that had set for a reset value. If we want to check again to see that the encryption key is being produced randomly at every runtime, Oops, my apologies. You can see that the encryption key here, 650 BEC, differs with 736F, etc. And that concludes the project demonstration.